Hi everyone. Today we will continue studying the equilibrium, which is one of the consequences of Newton's first law of motion. If in the absence of a net external force on an object, we know that object's nature is to maintain its state of motion. So we can define two states for an object. Object can stay at rest, or object can be in motion. So first law of motion describes that if the net force acting on the object is equal to 0, object will stay at rest if it is initially at rest. An object will be moving in a straight line path with a constant speed if it is initially in motion. So also this law, Newton's first law of motion, known as the condition for equilibrium. One condition of equilibrium. In the 12th grade, you are going to name translational equilibrium. So Newton's first law defines that if the net external force F net, or vector sum of all forces acting on the object, is equal to 0, so the body must be in equilibrium. And it is represented by this equation: vector sum of all forces acting on the object must be equal to 0. Then we say that object is in equilibrium, or specifically it is in translational equilibrium. And but sometimes forces can be inclined. If the forces are inclined, you need to dissolve the forces into components. In this case, you are going to add the components of the forces. Vectors, the sum of the components, x component of the forces will be equal to 0. This one is the sum of the x components of the forces will be equal to 0. Or sum of the y components of the forces will be equal to 0. So now I'm going to apply these two conditions to two simple problems. I will write two simple questions to make two problems to make understandable this title. First example is: calculate the magnitude and direction of the third force to keep the object in equilibrium. As you see in this problem, there are two forces acting on the object. One of them is F1, the other one is F2. F1 is in positive x direction, F1 is in negative x direction, but their magnitudes are different. So that's why this object will accelerate with a net external force if only these two forces act on it. But we want to keep this object in equilibrium, which means a third force must be acting on this object. So then this third force will keep this object in equilibrium. So because all the forces are along x-axis, I am going to use the vector sum of all forces along x-axis will be equal to 0. When you are writing the equation, these forces into equation, you should only care about the direction of the forces. If the force is in positive x direction, you are going to write this force into equation as positive. If the force is in negative x direction, you are going to write the force into this equation as negative. So as you see, F2 is in negative x direction. That's why F2 must be written as negative 2.4, but F1 is in positive x direction, so it must be written as positive 5.3. And we are going to add a third force to this system, which is unknown. I will find, and some of them will be equal to 0 because I want to keep this system this object in equilibrium. Then this operation is positive 2.9 plus F3 is equal to 0. Then if we take this positive 2.9 to the right side of the equation, so I can get F3 is equal to negative 2.9 newtons. And this negative sign in here indicates that this F3 must be in negative x direction. Then let's draw F3 on the diagram. So this is the diagram of the question when it is not in equilibrium. So I had to draw the third force in negative x direction and with a magnitude of 2.9. So negative direction, the third force must be in negative x direction and its magnitude must be 2.9 newtons. What if the forces are acting along y-axis? So calculate the magnitude and the direction of the third force to keep the object in equilibrium. Okay, two forces are again acting on this object in opposite directions, and one force is 3.8 Newton, the other one is 8.7 Newton. So then a third force, I will add this system a third force, and I will keep this system in equilibrium, this object in equilibrium. This time I am going to use the sum of the forces along y-axis must be equal to 0. I will use this equation because all the forces along y-axis. The forces in the positive y direction will be written as positive. The force which is in negative y direction will be written as negative into this equation. So 3.8 is in positive y direction, so I am going to write 3.8 as positive, but 8.7 Newton force is in negative y direction. I will write it into equation as negative, and I will calculate F3, which is unknown force, to make the net force 0, which is the condition for equilibrium. So this operation is equal to negative 4.6 plus F3 is equal to 0. After that, I have to take this negative 4.6 to the right side, so it's going to be F3 is equal to positive 4.9 Newton. This positive sign indicates that the F3 must be in positive y direction. If I draw the diagram, this is a diagram without the third force, so I have to add a third force into this system in positive y direction with a magnitude of 4.9 Newton, and then this system, this object, will stay in equilibrium. This is how we apply the equilibrium conditions to some problems. Then now I will solve some section review questions. The first one is one of the section review question number 2. It's talking about a car accelerating downhill under a net force of 3,674 newtons. So because it's accelerating downward, this net force, I will say this net force as F1, must be, of course, downward. Its direction must be in the same direction of the acceleration. So this system right now accelerates, but question is that I don't want this system to be accelerate because constant velocity. We want this system to have constant velocity. To have constant velocity means acceleration 0, which means net force acting and the object must be equal to 0. I have to make this net force 0. How can I do that? So let's say the force I am going to add this system. So I should add a force into this system to make the net force 0. I am going to add a second force in this system, and I will make the net force acting on the object is equal to 0. So because the forces are along x-axis, object accelerates along x-axis, so I'm going to use the sum of the force acting along x-axis must be equal to 0. And one of them is in positive x direction, F1 is in positive x direction, I will find F2. F1 is 3,674 plus F2, which is unknown, must be equal to 0. If you take this positive 3,674 to the right side as negative, so it will be F2 will be negative 3,674 Newton. This negative sign again indicates that this F2 second force must be in negative x direction, and magnitude of the second force must be 3,674 Newton. In this case, vector sum of these two forces will be equal to 0. And another question, if a car is traveling westward with a constant velocity of 20 meters per second, what is the net force acting on the car? Constant velocity, again in here, we don't care constant velocity 20, 10 or whatever. So if an object is moving with constant velocity, which means acceleration of the object is 0, if acceleration is 0, this net force acting on the object must be equal to 0, which is the first law of motion. So to have the constant velocity is defined by Newton's first law of motion. The net external force acting on the object must be equal to 0. Remember, there were two cases. If object is initially at rest, it will stay at rest. If initially it's in motion, it will continue moving with constant velocity. Question number 5, which is critical thinking. Can an object be in equilibrium if only one force acts on the object? Assume this is the object, consider this one, and one force is acting on this object, say that F1 gives some magnitude, which is say 100 Newton. So if one force acts on object, this only force, single force, becomes equal to net external force. If there's a net external force acting on the object, so object is not in equilibrium, because to make object in equilibrium, you should make the net force acting on the object is equal to 0. And this is the condition for equilibrium, more specifically translational equilibrium. So then, if only one force acts on the object, it is impossible to keep this object in equilibrium. So impossible. Possible is the answer. Okay, now we will continue with the one more problem. Problem number 3. The sensor in the torso of a car crash test dummy records the magnitude and direction of the net force acting on the dummy. Dummy is this model located inside the car to make some crash tests. And if the dummy is thrown forward with a force of 130 Newton while simultaneously being hit from the side with a force of 4,500 Newton, what force will the sensor report? So directions are forward, backward, left side and right side of the car. This is the top view of the car. And a force will be applied on the dummy in forward direction, which is equal to 130. So let's say this is F1. It will be in forward direction, F1 130. Simultaneously, at the same time, this dummy will be hit from side. You can hit it from right side or left side, it's up to you. If it is hit from the left side by another car, so then dummy will experience a second force towards the right side in that direction. So a force F2 will be acting on the dummy, which is equal to 4,500 newtons. Question is that what force will sensor report? So sensor will report the, of course, resultant of these two forces. So I have to calculate the resultant or net force acting on the dummy. I have to use vector addition method. So when I add F2 to the tip of F1, I will get this F net, which is the resultant of these two forces, and I can calculate its magnitude by using Pythagorean, which is F1 squared plus F2 squared square root. F1 is 130, F2 is 4,500, square of them. After that, get the square root. The net force acting on the dummy is 4,502 newtons. Then we can say that the sensor will report a net force which is equal to 4,502 newtons. And question number 4. What force will the seat belt have to exert on the dummy in item 3 to hold the dummy in the seat? So to hold it in the seat, which means the net force acting on the dummy must be equal to 0. It is the condition for equilibrium. But right now in this case, this green arrow is green vector is the net force. Net force is not 0. To make it 0, we need an additional force. So this force must be in the opposite direction of this net force and equal in magnitude. That's why belt must act a force on the dummy in the opposite direction of this net force and equal to that net force. That net force we calculated 4,502. That's why belt also must apply a force which is equal to 4,502 newtons in the opposite direction of the resultant of F1 and F2. Okay, this is all for the section 2. Now we define the condition for equilibrium. In the next lesson, we will talk about Newton's second and third law. See you next lesson.